Humanity could one day build a machine that captures the power of a star. This is the Dyson swarm, a colossal network of orbiting solar collectors designed to power our civilization for thousands of years. By the end of this video, you will possess the ultimate engineering blueprint to construct this stellar energy network yourself. We will uncover how to overcome the staggering challenge of building in deep space and what mysterious force could hold the entire structure together. What does it truly mean for a species to harness the energy of its sun? A vast celestial cloud, not of water vapor, but of countless mirrors and solar panels, perpetually orbits our star. This is the true vision of a Dyson swarm, a concept physicist Freeman Dyson proposed not as a rigid, solid shell, but as a dynamic and resilient constellation. Imagine each satellite as a single worker in a cosmic ant colony, each performing its own simple task, yet together creating something of immense power and complexity. This decentralized approach is its greatest strength. A single failure in one unit does not collapse the entire system, and new collectors can be added incrementally, growing the network over centuries. These individual energy collectors, potentially millions or even billions of them, would work in concert, focusing sunlight onto power conversion stations or beaming the harvested energy across the void. This transforms our solar system from a series of isolated worlds into a single, integrated engine, a power grid on a stellar scale. But such a monumental project cannot begin with finished satellites. The first and most crucial step is sourcing the raw ingredients, and our starting point is closer than you might think. The very first construction crews for this project would not be human. They would be robotic miners stationed on the airless, resource-rich surface of our moon. A robotic spacecraft touches down on the dusty, cratered surface of a near-Earth asteroid. Its mission is not to seek rare gems for earthly treasures, but to harvest the most valuable resource for our future, the raw materials for construction. This is the practical reality of in situ resource utilization, or ISRU, a principle that sounds complex but is beautifully simple. It means using what you find out there to build out there. The alternative, launching every single nut, bolt, and solar panel from the bottom of Earth's deep gravity well, would be so prohibitively expensive it would crush the project before it began. So we turn to the cosmos itself for our supplies. These wandering asteroids and our own moon become celestial quarries, rich with iron and nickel for structural frames, aluminum for reflective surfaces, and silicon for the heart of the solar cells. Even the water ice locked in permanently shadowed craters is a priceless commodity, not just for supporting human life, but as a source of hydrogen and oxygen for rocket fuel. This approach transforms inert space rocks into the very foundation of a dynamic, living energy network. As expert planetary scientists point out, this is not just an option, it is the only economically feasible path forward. To build among the stars, we must first learn to live off this celestial land. Once we have secured this endless supply of cosmic building blocks, we face our next monumental task, orchestrating the production of not just thousands, but potentially billions of individual units. This silent lunar factory never sleeps, its assembly lines humming under the stark contrast of black sky and sun-bleached regolith. Here, advanced robotics work in perfect concert, directed by an artificial intelligence that oversees every step from mining the raw ore to fitting the final panel on a new energy collector. The sheer scale of a Dyson swarm, needing not millions but trillions of individual units, makes this level of automation non-negotiable. Human hands could never build fast enough. The true breakthrough lies in what these robots are programmed to do next. They must be capable of self-replication, using the materials they harvest to construct not only the swarm components but also perfect copies of themselves. This creates a cascade of production, a workforce that grows exponentially from a single, sophisticated seed. This is the only way to achieve the staggering numbers required. The artificial intelligence governing this operation does more than just issue build commands. It manages an impossibly complex ballet of logistics, calculating the most efficient routes for raw material transport, scheduling construction, and solving problems in real time. It is the central nervous system of a growing industrial empire, ensuring that every gram of processed metal is used to its fullest potential. Humanity's role shifts from builder to conductor, setting the grand vision while the machines execute the symphony. The resilience of the entire Dyson swarm depends entirely on this self-sustaining, self-repairing industrial foundation in space. With such a powerful manufacturing engine in place, our attention turns to the product itself. What is the ideal shape and form for a single unit in this vast energy-gathering constellation? These individual energy collectors are marvels of minimalist engineering, gossamer thin structures kilometers across that must be both incredibly lightweight and remarkably durable. Picture a solar sail, a vast silver sheet thinner than a single human hair, but engineered to do more than just catch light. It must convert that light into usable power and withstand the relentless bombardment of micrometeoroids and the sun's own intense radiation. This is where advanced materials like carbon nanotubes and graphene composites come into play. Their molecular structure offers a strength-to-weight ratio that is almost unimaginable, allowing a collector to maintain its shape and function for decades without requiring a massive, heavy frame. The active surface might be a layer of ultra-efficient thin-film photovoltaics, or it could be a highly reflective aluminized film designed to focus sunlight onto a central power station. The choice between these designs is a fundamental trade-off. Do you build a decentralized network where each unit generates its own power, or a simpler, more reflective system that sends all its energy to a specialized converter? This decision impacts everything from the complexity of each satellite to the overall architecture of the swarm itself. The guiding principle is not merely peak performance, but what can be reliably and affordably manufactured in astronomical quantities. After all, the most efficient collector in the world is useless if you can only build a few of them. The perfect design is therefore an elegant balance, a product of materials science that prioritizes ease of production and longevity as much as raw power output. With our fleet of collectors designed and rolling off the lunar assembly lines, we confront the next great puzzle. How do you orchestrate the placement of trillions of these objects around the sun without them colliding into a cloud of cosmic debris? Maintaining this cosmic formation is a problem of physics and precision on an unimaginable scale. Each energy collector must follow a perfectly calculated path, a specific lane in an immense, invisible highway system encircling the sun. This is not a single flat ring like Saturn's, but a thick, multi-layered shell, with countless individual orbits set at different angles and distances. Think of it as a beehive, not with hexagonal cells, but with each bee tracing its own unique, non-intersecting loop around the central queen. The stability of the entire swarm depends on this intricate, three-dimensional choreography. If two collectors were to cross paths at orbital velocities, the result would be a catastrophic chain reaction, turning valuable assets into a cloud of shrapnel that threatens every other unit in the vicinity. To prevent this, sophisticated software acts as a universal air traffic controller, constantly monitoring the position of every single satellite. it makes tiny, preemptive adjustments to their trajectories, using minimal thrust to maintain safe distances. This system must also account for the subtle but persistent gravitational tugs from the planets, especially the massive pull of Jupiter, which could gradually distort these carefully planned orbits over time. Furthermore, this celestial roadmap must include designated clear lanes, open pathways through the swarm for spacecraft to travel safely to and from the inner solar system. This continuous, intelligent guidance is the silent, invisible force that holds the entire enterprise together. It transforms a potential chaos of flying objects into a synchronized, harmonious machine. But this intricate dance introduces a new challenge. How do you power the constant, small maneuvers required to keep trillions of units in perfect formation? This vast celestial machinery requires a mind to guide it, a central intelligence that can oversee the trillions of moving parts. Envision a decentralized digital nervous system, a network of control stations spread from the orbit of Mercury to the asteroid belt. This is the swarm's brain, a distributed artificial intelligence with no single point of failure. Its primary job is to maintain a constant, real-time dialogue with every single energy collector. It monitors their health, tracks their precise position down to the meter, and assesses their power output. When a unit's performance dips unexpectedly, the system doesn't wait for a human operator. It autonomously diagnoses the issue, whether it is a dust accumulation on a solar panel or a minor thruster misfire, and dispatches a tiny, specialized repair bot from a nearby depot. This is not a single supercomputer that could be lost to a random asteroid impact, but a resilient web of processing power. The failure of any one control node is instantly compensated for by its neighbors, ensuring the entire network remains aware and in command. This constant, intelligent oversight is what transforms a vast collection of independent parts into a single, cohesive, and intelligent whole. A critical and continuous task for this digital brain is managing the flow of power itself. It must constantly calculate the most efficient pathways to beam the harvested energy to where it is needed most, whether that is a growing colony on Mars, a scientific outpost on Titan, or a waiting starship preparing for its journey to the stars. This incredible feat of logistics brings us to the ultimate purpose of the entire endeavor, the question of what we actually do with all that power. The silent, invisible arteries of this stellar engine are not built of copper or steel, but of coherent light and precise microwave radiation. These are the power beams, the essential threads that stitch the entire Dyson swarm into a unified, functional whole. Without them, all the energy collected remains trapped in a shell around the sun, useless to anyone elsewhere. The principle is deceptively simple. At a specialized transmission station within the swarm, the raw solar electricity is converted into a specific form of energy, either a highly focused microwave beam or an incredibly precise laser. This energy is then aimed with the accuracy of a cosmic sniper rifle at a receiving station, or rectenna, which could be orbiting Mars on the surface of a moon or attached to a spaceship decades away. The rectenna's sole job is to catch this beam and convert it back into usable electricity. This technology transforms the abstract concept of a Dyson swarm into a practical, solar system-wide power grid. A research base on the dark, icy plains of Pluto could draw its warmth and light directly from the sun, delivered across billions of kilometers by this ethereal cord of energy. The engineering, however, is anything but simple. The beam must remain perfectly tight and perfectly aimed over these astronomical distances. A tiny fraction of a degree of drift could mean the beam misses its target entirely, wasting colossal amounts of power into the void, or worse, sweeping across a populated area with devastating consequences. This makes the guidance and safety systems the most critical components of the entire transmission network. The system would be designed with multiple, redundant layers of protection. Fail-safe mechanisms would instantly shut down a beam if its lock on the receiver was ever interrupted. Furthermore, the frequencies used for power transmission, especially microwaves, can be chosen to be inherently safe, passing harmlessly through atmospheres and any biological matter without interaction. This ensures that these rivers of power flow only where they are intended, making the space between worlds not a barrier but a conduit. With the power flowing reliably, we must confront the final and perhaps most profound challenge. How do we protect this civilization-scale achievement from the unpredictable hazards of deep space for millennia to come? The silent, invisible dance of trillions of collectors is a ballet of breathtaking precision where a single misstep could unravel everything. At the velocities involved, even a minor collision between two gossamer-thin units would not be an isolated event. The resulting debris cloud would create a cascade of further impacts, a chain reaction known as Kessler's syndrome, but on a scale encompassing the entire inner solar system. This scenario would effectively imprison our civilization, turning the space around our sun into an impenetrable, shrapnel-filled shell. Preventing this cosmic gridlock is not a secondary consideration. It is the paramount element that allows the swarm to exist at all. The blueprint addresses this with an integrated safety and debris management system of unparalleled sophistication. Every single collector is more than just a power generator. It is an intelligent node in a vast sensor network. Advanced radar and optical tracking systems distributed throughout the swarm maintain a constant, real-time map of every object's position and trajectory. Each collector is equipped with its own tiny, efficient propulsion unit, allowing it to make the minute course corrections necessary to maintain its designated lane in this immense traffic system. The central artificial intelligence acts as a supercomputer conductor, constantly running billions of simulations to predict potential conflicts years or even decades in advance. It identifies close approaches long before they become emergencies, issuing gentle nudges to the involved collectors to adjust their paths harmlessly. This proactive, predictive approach is the first and most critical layer of defense, but the system must also manage its own life cycle. Protocols for end-of-life operations are baked into the design from the very beginning. A collector reaching the end of its operational lifespan does not simply become drifting junk. It is either gently guided on a trajectory to plunge into the sun for final disposal, or it is moved to a designated graveyard orbit, a safe zone well away from the bustling activity of the main swarm. This continuous housekeeping is essential to maintain a clean, predictable operational environment for centuries to come. Safety, therefore, is not a feature added later. It is woven directly into the very fabric of the swarm's design and its daily operational logic. A safe swarm is a stable one capable of enduring for generations. Yet this long-term stability faces another profound test, one that comes not from within, but from the unpredictable nature of the cosmos itself. A celestial machine of this magnitude cannot afford to wait for a repair crew from Earth. The journey would take months, and by the time they arrived, a minor fault could have cascaded into a systemic failure. The swarm must heal itself. Circulating silently through the vast cloud of collectors are specialized drones, the medics and scavengers of this artificial ecosystem. They are the immune system of the Dyson swarm, perpetually on patrol, their sensors constantly scanning for the slightest anomaly in a unit's power output, structural integrity, or orbital stability. When a collector reports a fault or is flagged by the network's AI, the nearest repair drone is dispatched. It doesn't just diagnose the problem from a distance, it physically docks with the ailing unit. Using sophisticated robotic arms and onboard 3D printers that fabricate replacement parts on demand from stored raw material, it can perform surgery on a damaged solar panel, clear accumulated dust from a reflector, or replace a faulty guidance thruster. This is not a centralized repair shop, but a distributed capability with thousands of these mobile workshops operating simultaneously across millions of kilometers. But what happens when a collector is too badly damaged, perhaps from a micrometeoroid impact, to be repaired? This is where the scavenger drones come into play. They are the recyclers of this cosmic economy. A scavenger will carefully dismantle a derelict unit, systematically harvesting its valuable aluminum frame, its silicon cells, and its titanium components. These materials are then sorted, processed, and fed back into the manufacturing stream, becoming the raw ingredients for brand new collectors rolling out of the lunar factories. This creates a truly closed-loop system where very little is truly wasted. The swarm gradually learns to sustain itself from its own substance, drastically reducing the need to constantly mine new materials from asteroids. This perpetual automated cycle of diagnosis, repair, and recycling is the secret to the swarm's potential longevity. It is what allows this colossal structure to not only be built, but to endure, potentially operating for thousands of years with only minimal oversight. This self-sustaining health ensures a continuous, unwavering flow of energy, a river of power so vast it forces us to ask the ultimate question. What could a civilization possibly do with the total energy output of a star? The sun never sets on a Dyson swarm, but across the solar system, civilizations still sleep and wake, creating a rhythmic ebb and flow of energy demand that the swarm must master. This colossal network is more than a power plant. It is the beating heart of an interplanetary energy grid. Its ultimate challenge is not just generating unimaginable power, but storing and delivering it with the reliability of a city's electrical system. While the swarm itself basks in perpetual sunlight, planets like Earth and Mars rotate in and out of shadow, their cities and industries creating peaks of consumption that must be met instantly. To bridge this gap, the swarm employs massive orbital reservoirs. Envision colossal flywheels spinning in the vacuum of space, storing energy as rotational momentum, or vast facilities housing advanced solid-state batteries, charged during a planet's day and discharged during its night. For longer-term storage, excess energy could even be converted into stable chemical fuels like hydrogen, which can be shipped to the surface of Mars or stored in lunar depots, acting as a cosmic battery pack for cloudy days or increased industrial activity. This is where the grid management artificial intelligence truly earns its role as a cosmic energy broker. This digital overseer does not merely monitor power levels, it actively predicts them. It analyzes the industrial schedules of Martian colonies, the waking cycles of habitats orbiting Jupiter, and the energy consumption patterns of a traveling starship. It then performs a continuous, real-time auction of stellar power, routing gigawatts of energy across millions of kilometers to the highest bidder at any given moment. One instant, it might direct a power beam to a fleet of construction robots in the asteroid belt. The next, it could shift that flow to a research station on Europa, thawing a sample of subsurface ice. This intelligent distribution prevents the catastrophic waste of simply beaming power into the void when there is no one to receive it, ensuring that every photon captured is put to productive use. This transformation of raw, chaotic stellar fury into a steady, utility-grade resource is the final, crucial step in taming a star. It makes the power of the sun as dependable as turning on a light switch, whether you are in a domed city on Mercury or a subsurface ocean on Enceladus. And with that kind of reliable, limitless energy now flowing through the veins of human civilization, the very nature of our economy, our ambitions, and our place in the cosmos is forever altered. The staggering scale of this project demands an economic engine as resilient and self-sustaining as the swarm itself. Funding a Dyson swarm cannot be a single, massive withdrawal from humanity's collective treasury, but rather a patient, multi-generational investment that pays for its own growth. The blueprint calls for an international public-private partnership, a grand alliance where the very first trickle of power sold from space fuels the construction of the next collector. This transforms the endeavor from a fantastical expense into a series of manageable, profitable business ventures. It begins not with 1 trillion mirrors, but with one. A single prototype energy collector is launched and positioned to power a robotic mining operation on a nearby asteroid. The profits generated from selling the refined metals or water ice from that first asteroid then fund the construction of 10 more collectors. Those 10 power more extensive mining bases, and their profits fund 100 more. This slow but exponential growth model is the only financially viable path to risking the investment by proving the concept and generating returns at every single stage. Each new collector is a down payment on the next, building momentum and attracting further investment as the economic potential becomes undeniable. This gradual, self-financing expansion ensures the project is not vulnerable to the shifting political winds of any single nation or generation. The Dyson swarm, therefore, emerges not as a sudden monument, but as the ultimate expression of a new economic reality, one where the energy and material resources of the solar system are steadily and profitably integrated into a human economy. This foundational shift in how we fund our future will inevitably reshape every facet of human society, redirecting our collective priorities from terrestrial scarcity to celestial abundance. With a viable economic model established, the blueprint must account for the ultimate long-term challenge, ensuring this celestial machine can operate and evolve not just for centuries but for geologic time. This river of stellar power would fundamentally rewrite the rules of human civilization. The completion of a Dyson swarm does not just represent an engineering triumph, it signals the dawn of a post-scarcity age. In this new era, energy ceases to be a commodity to be bought and sold, becoming instead a universal utility, as abundant and accessible as the air we breathe. The very concept of cost undergoes a radical transformation. The price of any manufactured object, from a personal vehicle to a megastructure, would no longer be dominated by the energy bill for its creation, but solely by the value of the raw materials and the information, the blueprint, required to assemble it. This shift could dismantle the foundations of poverty that are rooted in resource inequality, offering every person on Earth, and eventually throughout the solar system, a baseline of material security that has been unimaginable for all of human history. What would humanity choose to do when the constant struggle for basic necessities is lifted? The answer could be a renaissance of unprecedented scale, a collective turning of our attention away from mere consumption and toward profound creation. We might see entire cultures evolving to value artistic expression, deep scientific inquiry, and pure exploration as their primary pursuits. The drive to compete for limited resources could be replaced by a shared mission to understand our universe and express our place within it. Yet this profound transition is not without its own set of intricate challenges. Legacy global industries built around the extraction and sale of finite energy would face an existential transition, requiring careful management to repurpose immense infrastructure and retrain vast workforces. The most critical question would be one of equitable access. How do we ensure that this new abundance uplifts all of humanity, rather than creating new forms of disparity between those who control the swarm's transmission nodes and those who do not? Navigating this new reality would demand a parallel evolution in our social and legal structures, forging a complex web of international agreements and cosmic laws to steward this power for the common good. This societal transformation, the redefinition of the human experience itself, is the ultimate purpose behind the entire monumental endeavor. It forces us to look beyond the physics and the engineering to the more profound puzzle of what we become when we finally hold a star in our hands. This immense power network demands a legal framework as advanced as its engineering, a new branch of interstellar law to prevent cosmic conflict. The first and most fundamental question is one of property. Who owns a specific orbital lane around the Sun itself? Without clear treaties, competing corporations or nations could lay claim to the most efficient orbital paths, creating a land rush in space that leads to disputes and potential sabotage. A transparent and fair system, perhaps administered by a reformed United Nations Office for Outer Space Affairs, would be essential to allocate these celestial real estate slots, treating the swarm not as a prize for the first to arrive, but as a common heritage of all humanity. This governing body would also need to establish clear liability protocols. If a power beam were to accidentally drift off target, even for a millisecond, who is responsible for any resulting damage? The legal framework must define negligence, establish insurance requirements, and create a process for arbitration that is recognized across the solar system. This turns potential chaos into a predictable, orderly system where all participants understand the rules, but the legal challenges extend beyond simple accidents. The very technology that beams life-giving energy could be repurposed. A focused microwave beam intended for a retina could, in theory, be redirected. This makes the prevention of weaponization a cornerstone of any interstellar treaty. The founding legal documents would need to explicitly ban the use of swarm components or their power transmission systems as offensive weapons, with robust and verifiable international monitoring to ensure compliance. The legal structure must also look inward, acting as a guardian for the solar system's natural environment. While the scale of the swarm is vast, its construction should not recklessly alter the delicate balance of our cosmic neighborhood. Regulations would be needed to assess the long-term impact of removing trillions of tons of material from asteroids and moons, and to ensure that the swarm's operation does not inadvertently affect the heliosphere or the light reaching distant planets. This legal and governance framework is not an afterthought. It is the social and political bedrock upon which the entire engineering marvel is built, a necessary system to ensure that this incredible power serves to unite our civilization, not divide it. The sheer complexity of a Dyson swarm introduces a universe of potential failure points, demanding a risk assessment on a scale never before attempted. Beyond the physical threats of micrometeoroids and orbital decay lies a more subtle danger: the risk of systemic collapse through unforeseen interactions or deliberate attack. A comprehensive analysis would categorize every conceivable threat, from the cosmic to the human. A powerful coronal mass ejection from the Sun, for instance, could unleash a wave of charged particles capable of frying the delicate electronics of millions of collectors at once. The network's central artificial intelligence, while essential, presents its own profound challenge. How do we ensure it never interprets its core directive to maximize energy collection in a way that conflicts with human safety? The solution is not to avoid these risks, but to engineer a system resilient enough to withstand them. This begins with a philosophy of deep redundancy. Critical command and control functions would not reside in one location. but be mirrored across dozens of independent stations scattered from Mercury to the asteroid belt. If one station were compromised or destroyed, another would instantly and seamlessly assume its duties, with no single point of failure capable of crippling the entire network. The swarm itself would be designed with isolated sectors, each capable of operating independently. In the event of a mysterious software anomaly or a localized crisis, entire segments could be placed into a pre-programmed safe mode, a stable, low-power holding pattern while the issue is diagnosed and resolved by human overseers. These manual override protocols are the ultimate safeguard. Secure locations on Earth, Mars, and perhaps hidden in the outer solar system would house facilities with the independent capability to transmit a universal stop command, a digital kill switch that would safely power down the swarm's active functions. This ensures that human judgment always remains the final authority. Cybersecurity becomes the silent, eternal guardian of this stellar engine. The command network would be a fortress, protected by encryption that is continuously evolved to stay ahead of any potential threat. Intrusion detection systems would monitor every data packet flowing through the network, looking for the faintest whisper of unauthorized access. A successful cyber attack could allow a malicious actor to hijack power beams or deliberately orchestrate collisions, turning humanity's greatest achievement into its most devastating weapon. Protecting against this is not an IT problem, it is a foundational requirement for civilization-level security. By planning for these contingencies from the very first design meeting, we weave resilience into the swarm's DNA. This proactive paranoia is what transforms a fragile megastructure into an enduring legacy, a system capable of protecting the civilization that depends on it for its very survival. Overcoming these immense challenges does not mark an end but a beginning. It unlocks the potential for projects that today sound like pure fantasy, ventures that the swarm's limitless energy would make miraculously possible. This vast network of power is not our final destination, but the very ground we must stand upon to reach for the stars. The true purpose of a Dyson swarm is to become the ultimate stepping stone, the foundational infrastructure that empowers humanity's next great leap. Think of the swarm as the first and most critical piece of cosmic scaffolding, the platform from which we can build endeavors of a scale that are currently pure fantasy. With a total energy output of a star at our command, what once seemed impossible becomes a matter of engineering. We could power massive interstellar propulsion systems, beaming concentrated laser light to light sails on generation ships as they begin their millennia-long journeys to neighboring star systems. We could initiate planetary-scale engineering, using focused mirrors to warm the thin atmosphere of Mars or power industrial processes to release gases trapped in its soil, slowly, over centuries, terraforming a new world for life. This energy could fuel particle accelerators built in the calm of space, rings large enough to encircle the orbit of Mercury, allowing us to probe the fundamental forces that shaped the cosmos. It could run supercomputers of such immense power that they could simulate entire ecosystems, model the birth of galaxies, or help us decipher the complex language of our own genetics. The swarm effectively transforms our entire solar system from a collection of isolated outposts into a single, integrated launchpad for the stars. It provides the raw power needed to transition from a single system species to a civilization that thrives across multiple suns. This perspective reframes the entire monumental effort. The Dyson swarm is not the grand finale of human engineering. It is the key that unlocks the front door of the galaxy. And to forge that key, we must first master the most fundamental art of all, the art of construction in the airless, unforgiving void of deep space. These orbital factories represent the final evolution of our industrial capacity, a leap beyond even the automated lunar foundries. In the deep silence of space, free from the relentless pull of gravity, the very rules of manufacturing are rewritten. Without gravity's constant downward tug, massive structures can be assembled from impossibly delicate components. Envision a solar collector the size of a city being constructed, its paper-thin panels unfurled by robotic arms without the risk of crumpling under their own weight. This is the promise of the zero-gravity workshop, an environment where the only limits are the strength of our materials and the ingenuity of our designs. The Dyson swarm cannot be built any other way. Its components are too vast, too fragile to ever be launched from a planetary surface. They must be born in the void where they are meant to live. This transition turns space from a harsh frontier we merely visit into a familiar workshop we permanently inhabit. The primary tool in this new workshop is advanced additive manufacturing, but this is far beyond the simple 3D printers of today. These industrial-scale fabricators use concentrated sunlight as their energy source, melting metallic powders harvested from asteroids to build up complex structures layer by microscopic layer. A single facility could print everything from the intricate gears of a repair robot to the kilometer-long spar of a new energy collector, all from the same stream of processed asteroid ore. This creates a truly closed-loop industrial ecosystem. The same robotic miners that gather the raw materials deliver them to the orbital factories. The factories then produce both the next wave of swarm components and the very ships and robots that will expand the mining and construction operations further out into the solar system. This self-reinforcing cycle is the engine of exponential growth, where the system's output directly fuels its own expansion. But this entire celestial production line depends on a single critical technology: the ability to move these gargantuan products efficiently across the vast emptiness between worlds. The efficiency of this entire cosmic workshop hinges on the silent, relentless work of its transport network. These silent cargo tugs are the workhorses of a new cosmic economy, gliding between the orbits of Mars and Jupiter on patient, efficient journeys. They do not rely on the violent, short-lived bursts of chemical rockets, but on the gentle, continuous push of advanced propulsion systems. Ion thrusters, for example, eject tiny, charged particles at velocities far exceeding any chemical exhaust, building up speed gradually over months like a steady breeze pushing a sailboat across an ocean. Nuclear thermal engines use the intense heat from a fission reactor to superheat a propellant like liquid hydrogen, creating a far more powerful and efficient thrust than traditional fuels. The economics of the entire Dyson swarm hinge on this leap in transportation technology. Hauling megatons of raw asteroid material across hundreds of millions of kilometers using conventional rocketry would be financially impossible, the fuel cost alone devouring any potential profit. Advanced propulsion slashes these transit times and fuel expenses, transforming the asteroid belt from a distant, inaccessible frontier into a reliable, local quarry for the inner solar system's construction sites. This creates a powerful, self-reinforcing cycle. The very first trickle of power collected by the earliest swarm prototypes is beamed directly to these cargo tugs, energizing their ion drives or powering their onboard reactors. This early energy output directly fuels the faster acquisition of materials, which in turn allows for the quicker construction of more energy collectors. It is a virtuous cycle where the project begins to fund its own exponential growth, each new watt of power catalyzing the creation of the next. The development of these robust and reliable in-space engines is not a secondary task. It is a parallel engineering track just as critical as the design of the solar collectors themselves. Without this affordable, high-capacity shipping network, the entire logistical framework of the swarm collapses. As we orchestrate this grand expansion into the cosmos, we must also cast a thoughtful eye back toward our own world, considering the delicate balance of the environment we are striving to transcend. A civilization that builds a star-encompassing machine must also become its steward, carefully weighing the consequences of its ambition. The very act of capturing sunlight on such a colossal scale introduces subtle but profound changes to our solar system's environment. While each individual collector in the Dyson swarm is nearly transparent, the collective effect of trillions of them forms a delicate, shimmering haze around the sun. This alters the solar system's albedo, its overall reflectivity, potentially casting a faint, permanent shadow over the outer planets. The delicate thermal balance that has existed for billions of years could be gently nudged, perhaps cooling the atmospheres of gas giants by a fraction of a degree over millennia. These are not immediate catastrophes, but long-term, cumulative effects that a responsible civilization must model, monitor, and manage. The blueprint, therefore, mandates continuous solar system-wide environmental impact studies, using a network of sensor platforms to track these changes in real time. This data would inform adaptive management strategies, perhaps by dynamically adjusting the density of the swarm in certain sectors to allow more sunlight to pass through, effectively using the swarm itself as a global thermostat to maintain equilibrium. This proactive stewardship ensures our quest for power does not inadvertently harm the very worlds we hope to one day call home. But the impact is not only physical, it is also philosophical. How do we ensure that in building a cage of light for our star, we do not build a cage for our own curiosity? The presence of this vast structure presents an unprecedented challenge for astronomy. From the inner solar system, the universe beyond would be permanently veiled by the brilliant, structured glow of the swarm itself. The faint light from distant galaxies would be utterly drowned out. The solution is a grand exodus of observation. Orbital observatories like the James Webb Space Telescope would need to be relocated far beyond the swarm's outer fringe, to the quiet, dark realms near Pluto's orbit or even further into the Kuiper belt. From these distant vantage points, the sun would appear as just another bright star, and the cosmos would once again open up in all its glory. Some visionary plans even propose building telescopes on the swarm's outer surface, using its colossal structure as a stable foundation for interferometers with baselines of millions of kilometers, allowing us to see the surfaces of exoplanets in other star systems. This demonstrates a core principle of responsible development, that our technological growth must always be paired with a commitment to preserving our window to the universe. This forward-looking responsibility extends beyond mere mitigation to the swarm's own life cycle. The initial design cannot be static. It must be a platform for continuous evolution. How does a civilization upgrade a machine that is already the largest thing it has ever built? The answer lies in the swarm's inherent modularity. New, more efficient collector designs would not replace the old ones in a single, costly overhaul. Instead, they would be introduced gradually as older units reach their end of life. Next-generation manufacturing pods attached to the orbital factories would produce these advanced models using materials recycled from the decommissioned ones. The swarm would thus undergo a perpetual, silent renewal, its capabilities growing steadily with each replacement, like a forest that slowly replaces its own trees. This capacity for graceful evolution ensures that the Dyson swarm remains a vibrant, growing partner to civilization, not a fossilized relic of a bygone era. It is a project that learns, adapts, and improves alongside the society it powers, a testament to a culture that builds not just for itself, but for the generations and the cosmos that will follow. This vast celestial machine is designed not as a static monument, but as a living, learning entity. its initial collectors, built with the finest technology of our century, will one day seem as primitive as stone tools. The true genius of the blueprint lies in its plan for perpetual renewal, a built-in mechanism for evolutionary upgrades and technological insertion. Over decades and centuries, the swarm must shed its old skin, continuously replacing outdated units with new models that harness the latest breakthroughs. The first generation of collectors, reliant on silicon-based photovoltaics, might be succeeded by a second generation using ultra-efficient multi-junction cells that capture a wider spectrum of sunlight. Later, these could be replaced by collectors that employ entirely new physics, perhaps based on artificial photosynthetic materials or even thermal conversion systems that operate at staggering efficiencies. This process is the swarm's immune system against obsolescence, ensuring it never becomes a fossilized relic floating around the sun. The key to this seamless evolution is the very modularity that defines the swarm's architecture. Each collector is an independent node, a single leaf on a vast celestial tree. When a unit reaches the end of its operational life, a specialized deconstruction drone does not simply discard it. It performs a careful autopsy, harvesting valuable components for recycling while logging the specific reasons for its failure. This data feeds directly back into the design cycle, informing the next iteration. The orbital factories then produce the new, superior models, which are launched into the same precise orbital slots recently vacated. This creates a constant, slow churn of improvement, a silent replacement cycle where the swarm's overall performance climbs steadily higher without any single disruptive overhaul. The system's distributed artificial intelligence manages this entire ballet, orchestrating the retirement of old units and the seamless integration of the new to maintain perfect power output and orbital harmony. This forward-thinking approach transforms the Dyson swarm from a single engineering project into a perpetual engine of progress, a platform that grows smarter and more capable alongside the civilization it powers. The ultimate legacy of this endeavor may not be the energy it provides, but the profound knowledge of how to build on such a scale, a blueprint that could one day be applied to other stars, seeding light and life across the galaxy. Our star would no longer shine with its natural light across the galaxy. Instead, it would glow with the distinct thermal signature of a vast, warm machine, a beacon of engineered heat that would stand out dramatically against the cold backdrop of space. This infrared fingerprint is what astronomers call a technosignature, an unmistakable marker of a civilization that has learned to build on a stellar scale. The moment our Dyson swarm becomes operational is the moment we graduate to a Type II civilization on the Kardashev scale, a classification that measures a society's ability to harness the total energy of its home star. This is not a quiet, private achievement. It is our species' formal introduction to the galactic community, a declaration of our presence written in the language of physics itself. This very act forces a profound shift in our perspective on the search for extraterrestrial intelligence. For decades, we have listened for faint radio whispers, hoping to catch a fleeting message. But a Dyson swarm suggests that the most detectable signs of advanced life may not be deliberate signals, but rather the colossal, unintentional byproducts of their energy infrastructure. A star consistently dimmed by an orbiting structure or glowing with the waste heat of immense industry would be visible across thousands of light years to any civilization with telescopes not too different from our own. This realization turns our gaze back outward with a new sense of purpose and a powerful new question. If we are now capable of building such a structure, what should we be looking for in the star charts? The hunt would focus on stars that exhibit anomalous dips in their visible light, paired with an excess of infrared radiation, a combination that nature struggles to produce on its own. Finding just one such signature would be the most monumental discovery in human history, answering the ancient question of whether we are alone in the universe. But this new perspective on the cosmic stage carries a deep responsibility. It demands that we cultivate a mindset of patience, foresight, and profound humility, recognizing that our engineering ambitions are now our interstellar identity. The blueprint for a Dyson swarm is ultimately a story about time itself, demanding a new kind of human patience that spans centuries. The engineers who lay the first cornerstone in a lunar factory will be long gone before their great-great-grandchildren witness the swarm's full power. This reality requires a fundamental psychological shift, moving our civilization away from quarterly reports and election cycles and toward a perspective measured in generations. We must learn to plant forests whose shade we know we will never sit under. The continuity of such a project cannot rely on a single government or a fleeting moment of collective inspiration. It must be woven into the very fabric of our culture through education, art, and shared stories that give every child a sense of ownership in a future they will help to build. The central challenge is not just technological but motivational. How do you maintain political and social will for an endeavor whose grandest benefits are 1,000 years away? The answer lies in a carefully designed roadmap of visible, celebrated milestones. The first beam of power delivered to a Martian outpost, the 1 millionth collector successfully deployed. The moment the swarm's output surpasses the entire energy consumption of Earth, each of these becomes a generational victory. These are not just engineering checkpoints, they are cultural touchstones, moments for a civilization to pause and say, "We built this." This psychological framing is as critical to the swarm's success as the tensile strength of its carbon nanotubes. It transforms an abstract, overwhelming goal into a series of tangible, achievable steps, creating a chain of purpose that links one century to the next. This long-term vision, in turn, must be continuously fueled by an unwavering commitment to research and development, ensuring that each new generation inherits not just a project, but a living, evolving body of knowledge. This relentless drive for improvement requires a global brain trust, a distributed network of human ingenuity dedicated to solving the swarm's endless puzzles. Universities, government laboratories, and private research firms would form a permanent alliance, their collective focus aimed at the thousands of technical challenges that such a project generates. This is not a passive endeavor that waits for breakthroughs to happen elsewhere. The very ambition of building a Dyson swarm actively propels progress in a dozen critical fields at once. It forces us to invent new materials that are stronger and lighter, to develop artificial intelligence with greater problem-solving capabilities, and to design robotics with unprecedented dexterity and autonomy. To fund this perpetual innovation engine, a small but consistent percentage of the swarm's earliest power revenues would be automatically channeled back into research and development. This creates a powerful, self-reinforcing cycle. The first trickle of energy sold finances the research that leads to a new, more efficient collector design, which in turn generates more power and more revenue to fund the next wave of innovation. This virtuous cycle ensures the project never stagnates, continuously driving down its own costs while boosting its performance year after year. The lifeblood of this entire distributed research network, and indeed of the swarm itself, is a single, critical capability: the ability to talk across the void. The silent, efficient operation of trillions of autonomous units depends on an unbreakable stream of data flowing between them. This demands a communication system of unparalleled resilience and bandwidth, a celestial internet built to span the entire inner solar system. Unlike Earth's internet, which relies on fragile undersea cables and local cell towers, this network must be wireless, decentralized, and immune to the delays of vast distance. Lasers offer one promising solution, creating tight, high-bandwidth data links between neighboring collectors, which then pass information along like a cosmic game of telephone. For longer-range commands, highly focused radio waves could connect distant control stations. The entire system would be woven together by a suite of dedicated communication satellites, acting as relay nodes to ensure that a command sent from a human operator on Mars reaches a repair drone near Mercury's orbit in a matter of minutes, not hours. This robust, multi-layered network is the digital nervous system that allows the swarm to function as a single, cohesive intelligence, turning a cloud of individual parts into a unified mind. This constant, silent conversation across the void is the lifeblood of the entire enterprise, a digital nervous system woven from light itself. The construction and daily operation of the Dyson swarm generates a flood of data so immense it dwarfs all the digital information ever created on Earth. Every single one of the trillions of collectors is constantly talking, sending streams of telemetry about its power output, structural health, and precise position. This ocean of raw information needs to flow reliably across millions of kilometers of empty space, connecting the robotic miners in the asteroid belt to the control stations orbiting Mars, and linking every part of the swarm back to human supervisors on Earth. To manage this, we must build an interplanetary internet, a communication backbone scaled to the solar system. The foundation of this network would be tight beams of laser light, creating super-high bandwidth connections between neighboring nodes. Think of it as a cosmic game of telephone, where data is passed seamlessly from one collector to the next, forming a resilient web where no single broken link can sever the connection. For longer-range commands, highly focused radio waves would bridge the vast gaps between planetary hubs. This multi-layered approach creates a robust and redundant system, ensuring that a command from a human operator on Earth can reach a repair drone near Mercury in minutes, not hours. This reliable, instantaneous communication is what allows for the swarm's most delicate maneuvers. It is the difference between a chaotic crowd and a synchronized ballet, enabling trillions of units to adjust their orbits in perfect harmony based on a single, universally understood data stream. Without this invisible architecture of light, the Dyson swarm would be little more than a silent, disorganized cloud of debris, its immense potential locked away by the simple inability to talk to itself. This communication grid, however, does more than just manage the swarm. It becomes the most valuable piece of infrastructure ever created, a public utility that connects all of human civilization across the planets. A student in a domed city on Mars could have a crystal-clear, real-time video call with their family on Earth with no perceptible delay, sharing discoveries as if they were in the same room. Scientific teams on distant moons could stream petabytes of geological data back to supercomputers on Earth for immediate analysis. This flow of information would bind our interplanetary society together, fostering a shared culture and accelerating innovation at a pace we can barely conceive. The very act of building the swarm gives birth to the nervous system that allows a solar system-wide civilization to think, feel, and act as one. This silent cosmic ballet demands a precision beyond anything humanity has ever engineered. To prevent trillions of collectors from drifting into chaos, each one must know its exact location in the void, down to the centimeter, relative to every other object across millions of kilometers. This requires a universal clock and a universal map for the entire solar system, a navigation grid far more accurate than any terrestrial GPS. The solution lies not in building a network of human-made satellites, but in looking outward to nature's own perfect timekeepers. We would harness pulsars, the rapidly spinning corpses of long-dead stars. These celestial lighthouses emit beams of radio waves with a rhythm so stable and predictable it rivals atomic clocks. By locking onto the unique pulse patterns from several of these distant sources, any spacecraft can triangulate its position with breathtaking accuracy, creating a galactic positioning system. This pulsar-based framework provides the common reference point that allows every collector, every cargo tug, and every control station to operate from the same exact page of the same cosmic map. It is the invisible foundation that makes the swarm's intricate orbital choreography possible, transforming a potential traffic jam of astronomical proportions into a perfectly synchronized flow. With every component now locked into its precise place by this celestial guidance, the swarm transcends its original purpose. It becomes more than a power plant. It evolves into a stable platform from which we can orchestrate even grander cosmic designs. The true potential of the Dyson swarm lies not in a single function, but in its capacity for endless reinvention. This stellar network can evolve into a multi-purpose platform, its secondary roles amplifying its value far beyond mere energy collection. Picture a cluster of collectors, their mirrored surfaces subtly reconfigured not to focus sunlight, but to act as a single, colossal eye. By linking them together through interferometry, the entire swarm can be transformed into a telescope of unimaginable power. Its effective lens would be as wide as the orbit of Earth itself, granting us the ability to see the surfaces of planets orbiting other stars, to watch alien weather patterns unfold in real time, and to peer into the hearts of distant galaxies with a clarity that redefines astronomy. This is just one of the roles the swarm could assume. Other collectors could be dedicated to communication, forming a permanent, high-bandwidth relay network that connects every corner of our solar system. A probe diving into the icy geysers of Enceladus or a crewed ship skimming the clouds of Jupiter could transmit its findings back to Earth with no delay. Their signals bounced flawlessly across this celestial internet. Perhaps most critically for our home world, segments of the swarm could be dynamically repositioned to act as a protective shield. During periods of intense solar activity, these units could be maneuvered to cast a temporary, strategic shadow over Earth, deflecting the worst of a coronal mass ejection and safeguarding our power grids and satellites from catastrophic failure. The benefits cascade back to Earth in more immediate ways. The advanced robotics perfected for autonomous repair and construction in space could revolutionize surgery, with microscopic bots performing procedures with superhuman precision inside the human body. The ultra-strong, lightweight materials developed for the gossamer thin collectors could lead to new forms of transportation, from incredibly efficient aircraft to next-generation medical implants. The distributed artificial intelligence managing the swarm's logistics could spawn new paradigms in computing, optimizing global supply chains or modeling complex climate systems. This multiplicative effect means the swarm pays for itself many times over, not just in energy, but in a torrent of technological progress that uplifts every facet of human life. Unlocking this vast potential, however, requires us to see the swarm not as a simple machine, but as a complex, adaptive system, a single entity whose behavior is greater than the sum of its trillions of parts. This digital twin of our solar system is a universe in a box, a perfect mirror world where engineers can play out the entire lifespan of the Dyson swarm before a single piece of metal is forged. Running on a web of supercomputers, this simulation is a living, breathing model that ingests every known variable. It calculates the gravitational pull of every planet and moon, simulates the pressure of solar radiation on vast collector sails, and models the intricate ballet of orbital traffic with microscopic precision. Engineers can introduce a solar flare of unprecedented strength to see how the swarm's power distribution network reroutes energy in response. They can simulate the cascading failure of 1,000 collectors after a meteoroid shower, testing the response time of the repair drones and the resilience of the communication grid. Every bolt, every beam, every line of code in the swarm's artificial intelligence is first proven here, in this risk-free digital laboratory. This exhaustive virtual testing is the ultimate form of foresight, transforming the unimaginable complexity of the project from a terrifying gamble into a managed, iterative process. It finds the hidden flaws, the unforeseen interactions, the tiny fractures in the plan that could, over centuries, grow into catastrophic failures. With the simulation running through millions of potential futures, the blueprint is honed to a state of near perfection, its every component validated against a universe of what-ifs. All the preparation, all the theory, all the digital dreaming finally condenses into a single, tangible act. The simulation gives its final approval, and the first physical mission receives its launch command. A single, unremarkable spacecraft sits poised on its launch pad, its hull gleaming under the distant sun. This is not a moon lander or a Mars rover, but something far more profound, the very first seed of a future forest that will encircle a star. Its mission is deceptively simple: to deploy a single, experimental energy collector in a high Earth orbit and prove that the core principles of the Dyson swarm actually work. This prototype is a miniature version of the final design, a delicate silver flower perhaps only 100 meters across, packed with experimental thin-film solar cells, a prototype microwave transmitter, and a suite of sensors to monitor its structural health against the harsh reality of space. For the engineers who have spent their lives on simulations, this moment is a leap of faith, transferring their perfect digital model into the unpredictable physical world. The successful unfurling of its gossamer structure, a process never before attempted at this scale, will be the first critical test. A single tear or a failed latch could mean starting over, but a perfect deployment signals that the path forward is clear. Once operational, its true work begins, generating a tiny but measurable stream of power. This first trickle of electricity, perhaps enough to power a single city block, is immediately put to work. It is beamed to a waiting orbital depot, and the revenue from selling this first batch of pure space-sourced energy is digitally earmarked for one purpose only: funding the construction of the next 10 prototypes. This creates the project's first self-sustaining financial heartbeat, transforming the Dyson swarm from a theoretical expense into a functioning, profitable business. The psychological impact of this success is immeasurable. For the first time, the abstract lines of a blueprint have a physical address in the sky, an object that can be tracked and whose power can be measured and sold. It becomes a symbol visible to the entire world, a tangible promise that humanity's greatest engineering endeavor is no longer a dream, but a process that has irrevocably begun. This single, small seed, successfully planted in the void, contains the genetic code for everything that will follow, proving that we can indeed learn to build with star stuff. That first seed unfurling in orbit proves the blueprint is alive. We have traveled together from a star-spanning vision down to the ignition of its very first spark, tracing a path through challenges that once seemed insurmountable. This journey reveals a profound truth. The Dyson swarm is not a distant fantasy reserved for a far future society, but a ladder of consecutive, solvable problems. Each rung, from robotic miners on the moon to self-healing orbital networks, is a challenge our generation can begin to tackle. The complete blueprint is therefore more than an engineering document. It is a manifesto for a new human destiny. It outlines a future where energy scarcity is a forgotten chapter in our history, replaced by an age of abundance that unlocks our potential for creation and exploration. This transition marks our collective coming of age as a cosmic civilization, a species learning to build with the very fabric of its solar system. The most vital ingredient for this future is not a special metal or a secret equation, but the sustained courage to dream across generations. It calls for a new kind of patience where we plant celestial orchards knowing we will never sit in their shade. This vision belongs to the dreamers and the builders, to the young minds who will look at the night sky and see not just points of light, but a constellation of construction sites waiting for their ingenuity. The ultimate energy network is no longer a question of if, but of when, and more importantly, of who. It awaits its architects. We would love to hear which part of this grand blueprint captured your imagination the most. Was it the self-replicating lunar factories, the cosmic power grid, or the profound societal shift? Share your thoughts in the comments and subscribe to join us as we continue exploring the next frontiers.